Hello, I would like to solve some questions, some exercises on second order linear to ordinary differential equations. This is based on the course in UNSW Math2019. First of all, in this recording, I will focus on homogeneous case. In this homogeneous case, it means that this fx function needs to be 0. So this is y is a function of x. So the second derivative, first derivative. So second derivative linear order of the differential equations such that this part is 0. If fx is non-zero, then we have the non-homogeneous case. I will solve examples on non-homogeneous case in another video. Okay, for the homogeneous case, we use characteristic equation. For characteristic equation, we substitute y is equal to e to the lambda x. It's like a general solution. When you take to the first derivative, you will have lambda e to the lambda x. When you take the second derivative, you will have lambda squared. So when you substitute these derivatives into the equation, you will have e to the lambda x times this kind of a polynomial. And this polynomial is called the characteristic equation of the ordinary differential equations of this type. So this is a quadratic polynomial. So for the quadratic polynomial, we have two roots. Lambda 1, lambda 2 are the roots of that one. And according to these roots, you will have solutions given by the formula. And the formulas are here. A and B are any real numbers here. So this is a general solution, as a formula for the general solutions of this kind of ODEs. Okay, if lambda 1 and lambda 2 are real roots and they are different from each other, so you have two distinct real roots, then the general solution for this function will be some constant exponential the root lambda 1x plus b, some constant e lambda 2x. So for finding A and B, you need the initial conditions. If the initial conditions are given in the question, then you will substitute and you will have two equations, two unknowns, and then you can solve for A and B. So that's the way to go. If you have lambda 1 and lambda 2, the roots are real, but they are the same, then the solution space are given by this equation. So that's A, e to the lambda 1x plus B, see there's a x here, there's no x here, there's a x here, if the lambda 1 is equal to lambda 2. And that is lambda 1 is the one root we have. So that's the equation. If we have another possibility, we might have complex roots. If we have complex roots, then the complex conjugate has to be the root as well, as we know. So alpha here is the real part of the complex number, and beta is the imaginary part of the complex number. And the formula for the solutions of this space will be given alpha x a cosine beta x. Alpha is the real part of the root, and the beta is the complex part, imaginary part of the root, right? And will be given in this part. A and B, any real numbers. If we have the initial conditions, we compute A and B. Okay, let's do an exercise on it, and let's look at these three possible cases. Homogeneous case. So these are the equations that we are going to solve, homogeneous equations, and second order linear ordinary differential equations. Okay, the first one, we have 2y prime plus y prime minus 6y. As I said, if you put y is equal to e to the lambda, y prime will be lambda e to the lambda x, and y2 prime will be lambda squared e to the lambda x. And substitute in this equation will give us this equality. So e to the lambda x cannot be 0, so this needs to be 0, which is the characteristic polynomial. Characteristic polynomial is 0. We want to find out the roots of this polynomial. And one of the easy way to find out the roots of a polynomial, second quadratic polynomials, are writing down as a linear factors. So we can write this in these linear factors. Once you write it down, please check. Please exactly check. Even though you're sure about it, please check your calculations like we are going to do here. So 2 lambda will be times lambda, 2 lambda square, minus 3 lambda, and that's that. Then we have 4 lambda, that's that. And then we have minus 6. So 2 lambda square plus lambda minus 6, which is the equations that we have. So from the first linear factor, we have the lambda 1, which is the 1 root, is 3 over 2. From the second one, we have lambda 2 is equal to minus 2. So we have 2 distinct roots, and they are both real. For that, we have the formula that is given, the solution space is given by this formula. A and B are any real numbers. The first lambda 1 is 3 over 2, substitute 3 over 2. And the second root is minus 2, substitute minus 2. So that's the solution space, general solution for this linear system, to second order linear ordinary differential equation. Okay, now let's move on another question. So this is an equation that we would like to find out. We will calculate the characteristic polynomial. So that will be lambda square plus 4 lambda plus 53. So if you have a quadratic equations, A is like ax squared plus bx plus c is equal to 0. The solution is given by we calculate the discriminant, which is b squared minus 4ac. And then the roots of this polynomial are given by the formula minus b minus plus root discriminant of 2a. We know this formula very well from our even high school. Yeah, so we need to use this in order to be able to calculate the roots of this polynomial. And we calculate a discriminant that is b squared. B here is 4 squared minus 4 times 53, 4 times that. Then you have 16 minus 212. That will be the minus 196. So this is negative. So when we take the square root of it, that will be a complex root. It will tell us that that's complex root. So the square of the discriminant will be the square of 196 will be 14. And we have the square root of minus 1 will be just I, as we know. So the two roots, two complex roots, one and complex conjugate each other. So that's minus b minus plus the square root of discriminant, which is the minus plus 14i. That's what we calculated here. Divided by 2a. A here is 1, so that's 2. So we have too many 2's from the numerator and denominator. We will cancel out. Then we have minus 2 minus plus 7i. So these are the roots, complex roots for the characteristic equations. Yeah. Now this minus 2 is the real part of the root, and minus plus 7 is the imaginary part. We only think about the absolute value, just 7. So we have e to the alpha. Alpha is minus 2 for our case, and beta is 7 for our case. So that's the formula is given to us. So e to the minus 2x, a cosine 7x plus b sine 7x will be the solution for this equation. Okay, we've done the different roots, different real roots. We've done the complex roots. Now let's examine, do a little exercise on multiplicity 2, a root with multiplicity 2. So this is the question in that case in our hand. So the characteristic polynomial will be lambda squared minus 4 lambda plus 4 is equal to 0. We can decompose these quadratic equations into 2 linear factors. That's lambda minus 2, lambda minus 2. So basically lambda minus 2 square. So that is lambda is equal to 2 is 1 root with multiplicity 2. Okay, so in this case, the formula will be given in this way. We have only 1 root, which is 2. So the general solution will be y is equal to a plus bx e to the 2x. Okay, we need to know how to calculate the homogeneous part before we work out the non-homogeneous part, because that will be the next in the next video. That's what I'm going to talk about. If So this is the case when fx is equal to 0, non-homogeneous case when fx is non-zero. And if the equation is non-homogeneous, we also calculate the homogeneous part and then the non-homogeneous part. So we need both for the non-homogeneous case. We need to know this, how to solve this problem in order to be able to solve non-homogeneous case. That's my point. Okay, thank you.